Good morning, ladies and gentlemen. Our next topic for AP Physics is electrostatics. And when we think about the word electrostatics, we have to wonder, what are we really talking about? When do we really see static electricity? Well, the term static itself, of course, means stationary. And when we think about the word electricity, we should automatically think about electrons. So, whenever we talk about static electricity itself, or electrostatics, we're talking about the interaction of extra electrons, or a deficiency of electrons, that are acting upon each other. We're not talking about current electricity, which is what powers your light bulbs and your television. We're talking about instances when you might develop a buildup of some sort of charge, similar to this animation over here. We have a person walking along a wool carpet. As he's walking, the friction between his feet and the ground is leaving behind electrons. So he actually ends up being slightly positively charged. And when he touches the doorknob, zap! It's just like whenever you take clothes out of the laundry, whenever you rub a balloon on someone's hair, the friction creates a buildup of some sort of charge. And the release of that buildup is what creates what we know as static electricity. Now, we of course have already learned that there are two types of charges, a positive charge and a negative charge. Like charges repel, opposite charges attract. But where do we get these definitions for positive versus negative? What exactly carries a positive charge? What carries a negative charge? Well, the ancient Greeks were the ones who first came up with these definitions, when they noticed that when you rub certain types of materials on other materials, it developed this charge. And when you brought those two like charges together, they would repel. And that overall, there are two types of charges that they could create. And so they called one positive and one to be negative. The ancient Greeks had no idea whatsoever about protons, neutrons, and electrons at the time. They just knew that there are two types of charges. Let's go back for a second. So if you take a quick look at this demonstration over here.
Carried by a proton. When two objects are rubbed together, a transfer of electrons takes place. The object that loses its electrons becomes positively charged, while the object that gains electrons becomes negatively charged. On the basis of what we have seen, when a glass rod is rubbed on a silk cloth, a transfer of electrons takes place.
Now notice that these negative charges went onto the cloth itself. Okay? That means the electrons left the rod and went onto the silk cloth. Now, because those negative charges went onto the silk cloth itself,
glass rod loses its electrons and develops a positive charge.
Right, so the glass rod develops a positive charge.
If a positively charged glass rod comes in contact with a pith ball, it shares some of its positive charges. The rod conversely, when an ebonite rod is rubbed on a flannel cloth, the rod develops a negative charge.
Because
this
now
means
you can see
that
we
the
have
ebonite
negative
rod
electrons
has
are
gained
leaving the flannel
electrons.
cloth, and they're going
If a
onto the flannel
negatively
cloth.
charged ebonite rod comes in contact with a pith ball, it shares some of its negative charges. The pith ball develops a negative charge
This is
and is
known as
repelled by the ebonite rod.
conduction. Okay, and we'll talk more about conduction in a moment.
Let us see what happens when opposite charges are brought together. If the glass rod is brought near the ebonite rod, it is found that the two rods attract each other. Similarly, the two pith balls charged by the rods also attract each other.
Okay. So that overall, the plastic strip, or really the ebonite rod, gained a negative charge because it gained extra electrons, while the glass rod carries a positive charge because it loses electrons. Notice in both cases, protons do not move. Any sort of creation of positive or negative charge is entirely created by electrons, either by having extra electrons or a deficiency in electrons. And after being rubbed by fur or by the silk cloth or whatever it might be, the plastic ruler now carries a -5 charge, which meant that 5 extra electrons, we'll assume that for now, went onto the plastic ruler. But what charge does the fur now have? So if you have that fur and you have that rod and we have 5 electrons jump off, the rod has a charge of -5 electrons. Of course, since the fur lost electrons, it has a charge of +5 electrons. This is known as conservation of charge. Okay? If the glass rod had lost 150 electrons, it would have a charge of +150 E, while the fur would have a charge of -150 E. Okay. And of course, when you charge something, understand that things don't really remain charged forever, but that's mainly because the atmosphere itself, we have gas molecules that will come over and they'll grab those extra electrons or deposit the electrons if they're needed onto the charged shape itself. Okay. What is a conductor? A conductor, of course, is something that easily conducts electricity or heat, actually, okay, which we had learned in the previous unit. But the reason it conducts the electricity so easily is because of what you guys have learned about metallic bonds in chemistry. Mainly that metallic bonds you have a sea of electrons. The electrons are freely able to move around, and when they are directed by some sort of electrical field, which we'll learn more about later on, those electrons will easily move from one place to another. While an insulator, of course, is something whose electrons are more firmly attached. Okay? And so far in the examples you've seen with the plastic rod or the glass rod, those are insulators, but as you can see, they can still easily become charged. It's just that it's easier to see what happens to the electrons inside a metal. In fact, if we were to have a neutral metal sphere of some sort, neutral meaning that you have the same number of protons and electrons, if you were to bring some sort of charged rod towards a metal sphere, the electrons are so mobile that you can actually influence where those electrons are going to be. Whether you bring a positive charge over or a negative charge over, you can see that the protons themselves will always remain in place, but that the electrons are free to move around. And when they are free to move around like that, they end up creating a dipole, meaning that when this negative charge is over there and all these electrons are at the bottom, when all the electrons are at the bottom, you end up with a negative charge where all those excess electrons are. Or if the electrons vice versa move to the top, then you have an excess negative charge where they moved to the top. So if we were to illustrate that a little better, when you bring a positively charged object near a conductor, the electrons are attracted to that positive charge, meaning that the left side of the conductor is now more negative, while the right side is more positive. It's still neutral, but there's a dipole. And vice versa, if you brought a negatively charged object near a conductor, the electrons, since they are like charges, they end up getting repelled by that negative charge, creating an opposite dipole where it's negative on the right and positive on the left, but still neutral. Now, this happens to be true whether it's a conductor or an insulator. It's just that it's easier to see inside a conductor. Let's see. So over here, with an insulator, you can see that the electrons are still moving a little bit, but not so much that they'll go far away. But because they do move here, how do charged insulators affect neutral objects? Well, you've seen this before with the person who has a balloon. He rubs the balloon on his hair. Through friction, electrons are taken off and they're deposited onto the balloon. And when you stick the balloon onto the wall, it creates a dipole in the wall where it's negative on one side and positive on the other side. Because the positive charge is closer to the negative charge, now it's going to attract. So the fact is, all neutral objects, all neutral objects are automatically attracted to a charged object. Okay? All neutral objects are automatically attracted to a charged object. Okay. That's so in the end, if I were just to draw this over here, the electrons don't move so far away as they would in a metal, but enough so that there's still a slight dipole that the balloon will stick to the wall. This is even more obvious if we look at the example of the pith ball. Now over here, you can see there's a negatively charged rod. On the right-hand side, we have a neutral pith ball. But when you bring that rod closer and closer, you can see that the pith ball actually ends up being attracted. Why is the pith ball so attracted to the charged rod? Well, that's simply because of the dipole that's formed. A lot of the electrons are pushed over, they're repelled, and the leftover positive charges are closer, so they attract to that negative charge. This, by the way, I forgot to mention, is called induction, which is basically the redistribution of charge by a nearby charged object. Okay? And the most important thing, of course, is that during induction, there is no contact whatsoever between the charged rod and the pithball, or whatever it might be. Because if there was contact, well, that wouldn't be induction anymore. That would be what we call conduction. And with conduction, we have a transfer of charge. Conduction, there is contact, which thereby creates a transfer of charge. A lot of those extra electrons jumped onto the pithball, which made the pithball negative. Now, of course, a negative charge will repel another negative charge, which is why the pithball is now repelled. Now, even if I reset this entire thing and I use a glass rod instead, a glass rod is positively charged, which means that it is missing electrons. Now, if I bring the glass rod closer and closer, I still have a dipole. But now, the negative charges are now left, and which are closer to the positive charge. And when you touch through conduction, a lot of those electrons jump over onto, a lot more electrons jump off the pithball and jump onto the charged rod, which leaves the pithball positively charged, and a positive charge will, of course, attract, will repel another positive charge. Okay. So we saw conduction, where a neutral object, if you touch a positively charged object to a neutral object, some of those electrons are going to jump off onto the positive rod, thereby leaving that neutral object with more protons than electrons. So therefore, it ends up being positively charged. Okay, conduction has contact. Charging by induction is a very special case. Normally, between induction, there's absolutely no contact whatsoever, so there can be no transfer of charge. But if you have a special case that looks like this over here, we can see that when a negatively charged object is brought close, it creates a dipole. And when it's touched on one side, those electrons can get pulled out, leaving the object to be positively charged. So whenever you charge by induction, if this was, let's say, a positive object, okay, going towards a neutral object, the object itself ends up gaining the opposite charge of whatever you're charging it with. But if you're charging it with conduction, it ends up gaining the exact same charge. So charging by conduction, the object gains the same charge as the rod, while charging by induction, the object gains the opposite charge of the rod. Okay? So, conduction versus induction. Okay. Now, we've been talking about electrons and how when you gain electrons, you become negative, and when you lose electrons, you become positive. But what exactly are electrons, and what does it mean when I say that it's going to be quantized? You see, every electron has a specific charge, okay? And which scientists, or really Robert Millikan, had quantized as the charge of one electron, Q, which represents charge, of one electron is equal to 1.6 times 10 to the negative 19 coulombs. Now, when I say the charge of electron, that's also the same charge as a proton. Protons and electrons have the exact same charge. It's just that one is a positive charge and one is a negative charge. So whenever I use the word elementary charges, I could be referring to either electrons or protons. Now, the fact that charges are quantized, that means that every charge is created by a specific number of electrons. And we can use the formula Q equals NE to think about that, meaning that N is the number of electrons, or number of elementary charges, and E is equal to the charge of one elementary charge, or electron, which is 1.6 times 10 to the negative 19 coulombs. Q would be the total charge. So, for example, if a balloon has acquired a charge of negative 3.2 times 10 to the negative 17 coulombs, how many electrons does that really represent? And Q equals NE is really just a ratio. So if I have 3.2 times 10 to the negative 17 coulombs, I know that one electron is 1.6 times 10 to the negative 19 coulombs. Then, therefore, if I divide this out, this would equal to exactly 200 electrons. Okay, so this Q equals NE is really just a conversion factor that we can now use to determine how many electrons are in any single charge. Very common Regents question when they ask you, which of the following charges is not possible? And the easiest way to go through this is to actually find out how many electrons are within each charge. For example, with 5.6 times 10 to the negative 19 coulombs, if I put that over 1 electron is equal to 1.6 times 10 to the negative 19 coulombs, which means that in the end I have 3.5 electrons. Now, is it possible, though, to have half an electron? And you would see, of course, the answer is no. So therefore, A is not possible. If you take a look at B, 9.6 times 10 to the 17, negative 17, one electron is 1.6 times 10 to the negative 19 coulombs, and you end up with an answer of 600 electrons, which is a whole number. So B is possible. If you did C, you would see you'd have 0.2 electrons, which is of course not possible. And for D, you would see you'd have 1.5 times 10 to the 5th electrons, which is perfectly fine. So anytime you have a charge that's smaller than 1.6 times 10 to the negative 19, that's automatically not a possible charge because every charge is made up of a whole number of electrons. And that's what quantized means. It means that there is a specific quantity of electrons. If you have 1 coulomb of charge, by the way, a coulomb is the unit for charge. then I know that one electron is 1.6 times 10 to the negative 19 coulombs. Therefore, I can find out that I have 6.25 times 10 to the 18th electrons inside 1 coulomb of charge. So, whenever we talk about conduction and about the transfer of charge from one object to another, we're talking about transferring a specific number of electrons, a specific amount of charge from one object to another. For example, if we have a neutral sphere with a sphere that has an excess of 4 electrons, so 1, 2, 3, 4 extra electrons, so negative 4e. That means that when I touch the two of them together and I separate it, 2 of those electrons are going to jump over onto that neutral sphere. And you end up with 2 electrons on each side. So in this case over here, we have negative 2e, but the exact charge on each sphere would be, so 2e over 1. 1 electron is 1.6 times 10 to the negative 19 coulombs, which equals to 3.2 times 10 to the negative 19 coulombs. And that would be the exact charge on each sphere whenever I have conduction. If we take a look at the next example, sphere A has 30 excess electrons on it. What charge does it carry? Well, 30 electrons. 1 electron is 1.6 times 10 to the negative 19 coulombs, which would equal to 4.8 times 10 to the negative 18 coulombs. And if you touch another uncharged sphere briefly, assuming it's the exact same size, then it's going to split up its charge and give some to the other one. So then each sphere would then each have 15 extra electrons, and each sphere would have a total charge of 2.4 times 10 to the negative 18 coulombs. Negative, of course, because you have extra electrons. Even if we look at the last example now, 4 uncharged spheres are placed side by side. The first one has an excess of 40 electrons. If you touch the first 2 together, it becomes 24 and 24. You touch the next 2 together, you end up with 12 and 12. And if you touch the last 2 together, you end up with 6 and 6. So if I was to look for what's the total charge on the last sphere, 6e, 1 electron equals 1.6 times 10 to the negative 19 coulombs. So the total charge would equal to 9.6 times 10 to the negative 19 coulombs.